All right, folks, I do want to welcome you back to Unit 10. This is thermochemistry. We've kind of gotten the basics of this unit under our belts now. And what we want to do is focus now on some more advanced topics in thermochemistry. And so this is going to be intended really for pre-AP and advanced placement students, although anyone is welcome to follow. So let's go ahead and get started. So here we go. Using bond energies to calculate changes in enthalpy. Now we've said that the change in enthalpy can be symbolized by this delta H. And if it was positive, it was endothermic. If it was negative, it was exothermic, right? But I want to talk a little bit about how these numbers are arrived at. So when somebody says that the delta H for a chemical reaction is minus 437.6 kilojoules of heat, where does that number come from? Well, as it turns out, it comes from something called bond energies, and that's new today. What we want to do is look at what we mean by a bond energy. Well, what we do know is that for any chemical that there are bonds, right? So for example, if I look at, let's do a simple one that we're all familiar with, water, there are two HO bonds in this molecule. And there's a certain amount of energy associated with those bonds. In other words, a certain amount of energy that would be released if I were to break those bonds, and a certain amount of energy required to make those OH bonds. And we call that energy the bond energy, right? The bond energy. Now that's an HO bond. And the bond energy for an HO bond is going to be different than, say, an HH bond for hydrogen gas, and would be different still for something called oxygen gas. This is the Lewis structure for oxygen gas. So to break this oxygen-oxygen double bond is going to require a different amount of energy than it would be to, say, break a hydrogen-hydrogen bond. So where do we go to find out what these bond energies are? Well, we go to a bond table like this one. So this table lists bond energies associated with a number of different bonds, right? So for example, a hydrogen-hydrogen bond is going to have a bond energy of 436.4 kilojoules per mole. In other words, if I wanted to break a hydrogen-hydrogen bond, I would have to provide 436.4 kilojoules of heat for every mole. So if I had 2 moles, I'd have to double that. If I had 10 moles, multiply it by 10 and so forth. Now, as you can see, that's going to be different than, for example, a hydrogen-nitrogen bond, 393 kilojoules of heat per mole and so forth. So I've got a number of different bonds listed here, and I can use this information to determine what the delta H is for a chemical reaction, all right? So, but let's remind ourselves that bond breaking is an endothermic process. When you break a bond, you must provide energy to break a bond, right? But bond formation is an exothermic process. When you form a bond, you release energy. All right, so here we go. Let's take a look at this problem right here. We want to calculate the enthalpy change, in other words, the delta H for the following reaction. So we've got 2H2 plus O2 yields 2H2O. And again, we want to know delta H for this reaction. It's not just given to us. We have to calculate it using bond energies. Well, in order to do this, what we're going to need to do is recognize what really is happening in this reaction. So let's take a look at the reactants. We've got H2. So hydrogen is bonded to hydrogen, and we've got 2 of those, right? We've got 2 of those. Let me draw it just like that, okay? So in order for this reaction to happen, both of those hydrogen-hydrogen bonds have to be broken. So we're going to need to know what the energy requirement is for the breaking of those 2 moles worth of hydrogen bonds. Likewise, we're going to have oxygen, and that oxygen is bonded to another oxygen, just like that. That's the oxygen gas that you see right there on the reactant side. And we're going to require a certain amount of energy to break that oxygen-oxygen double bond. Now, on the product side, we're going to get, so we took those 2, those are going to be broken, those bonds are going to be broken, but then they're going to be reformed. They're going to be rearranged. Rearranged into what? Well, they're going to be rearranged into water. But not just 1 mole of water, 2 moles of water, just like that. So what's really happening here is that we're taking the 2 moles of hydrogen gas, breaking those 2 bonds, we're taking the oxygen, breaking that double bond, and then we're forming 1, 2, 3, 4 hydrogen oxygen bonds on the other side, on the product side. So to break apart the 2 hydrogen molecules is going to require 436.4 times 2 kilojoules of heat. Where am I getting this number? Where did the 436.4 come from? Well, let's take a look at the bond table. So I'm told, this is the very first entry, that a hydrogen-hydrogen bond has a bond energy of 436.4 kilojoules per mole. 436.4 kilojoules per mole. But there's 2 moles, right? There's 2 hydrogen molecules, or 2 moles of hydrogen molecules, and so I have to double that number. So 436.4 times 2. That's kilojoules of heat. Now the bond between the oxygen atoms is O2. It's a double bond, right? It's a double bond. So the energy required to pull these atoms apart is 498.7 kilojoules. Now we'll have to be a little bit careful here because there is such thing as an oxygen-oxygen single bond. As you can see, it's on the right-hand side. It requires 142 kilojoules per mole only to pull an oxygen-oxygen double bond, single bond apart. But it requires much more. In fact, double bonds always require more energy than single bonds for reasons we'll talk about later. And by the way, triple bonds are even more. But the point is that to break apart an oxygen-oxygen double bond is going to require 498.7 kilojoules of heat. We got that from the table, right? So, again, the energy required to pull these atoms apart is 498.7. Now, the HO bond has a bond energy of 460 kilojoules per mole. So remember, there are 2 of these bonds in a single mole of water molecules, and there are 2 moles, right? Therefore, we're going to multiply 460. Again, where did the 460 come from? Let's go back to the table and look for HO, and it is right here, okay? But remember, we're going to have to take that 460. In a single water molecule, there's 2 HO bonds, and then there's 2 moles of HO on the right-hand side. So we're going to have to multiply that 460 by 2, and then by 2 again. So 460 times 2 times 2 kilojoules of heat are released when these bonds are formed. Again, released when the bonds are formed. In other words, it requires energy to break bonds, but you get energy released. Energy is released when bonds are made. So let's finish up our calculations. To calculate the enthalpy delta H for this reaction, we'll determine the total amount of energy required to break bonds on the reactant side and the total amount of energy on the product side of this reaction. So to break the 2 moles of hydrogen bonds on the left, on the reactant side, we're going to need, again, 2 times 436.4 kilojoules of heat. According to my calculator, that's 872.8 kilojoules. Check me on that calculation, please. Now, to break the moles of oxygen atoms, right? To break the moles of oxygen atoms in the O2, we're going to need 1 times 498.7 kilojoules of heat. That's 498.7. So now let's add those up. My calculator gives me 1,371.5, right? 0.5 kilojoules. So that's how much energy is required. 1,371.5 kilojoules of heat are required. Now let's determine how much energy is released when the bonds on the product side are made, released on the other side. So that's how much energy is required to break bonds on the left side. How much is released when we make bonds on the right-hand side? To make the OH bonds in the water product molecules, remember it's 2 times 2 times 460, or 4 times 460. that gives me 1,840 kilojoules released, right? Now, this is very important. Because energy is released, given away, we're going to put a negative in front of it. So on the left-hand side, bonds were being broken. That required energy, so we put a positive on that number. So the 1,371.5 had a positive sign in front of it. But this time, energy is being released, so we're going to put a negative in front of it. Okay? So now we'll just add these together. So here we go. We've got positive 1,371.5 kilojoules of heat plus a negative 1,840 kilojoules of heat, and my calculator gives me negative 468.5 kilojoules of heat. All right? So this process results in the release of 468.5 kilojoules of heat, and this is an exothermic process. So what have we done? In this video, what we've done is we've taken bond energies and we've used these bond energies to calculate the delta H for a reaction. Remember, on the left-hand side, bonds are being broken. That means that the energies associated with those are positive. But on the right-hand side, bonds are being made. That means energy is being released. Those bond energies are negative. We simply take the reactants energies and the products energies, we add those together, and it's going to give us the total delta H for the reaction. Again, in this case, it was a negative. After all had been said and done, there was a negative on the solution. That means that this process is an exothermic process, right? An exothermic process because after all the bonds were broken on the left-hand side and the bonds were made on the right-hand side, and after we took into account that there were different numbers of moles for reactants and products, then 468.5 kilojoules of heat were released. Again, an exothermic process. That'll do it for this one. I'll see you in the next. Thanks. Bye-bye.